Okay, so there's a live transcript at the bottom in case people want to see it. If you don't want to see it, you can switch the button off. This is being recorded. If you wish to ask questions, you can ask questions in the chat or wait until the recording has been switched off at the end and then ask questions then. Okay, so we're very pleased today to welcome Scott McCue from QUT, who's going to speak on Kelvin ship waves and a bit of exponential asymptotics. So Scott gained his PhD in applied maths from the University of Queensland back in 2000 under Lawrence Forbes. He then went on to be a postdoc research fellow with John King and David Riley at Nottingham for a couple of years before going back to Australia and doing a postdoc research fellow at University of Wollongong, finally moving on to become a lecturer at Griffiths and then progressing in 2007 to QUT. Scott has been awarded several prizes for the work he's done in the general areas of applied maths he works in. Most recently, the Ernie Tuck Medal for research and services to ANZIAM. He's no stranger to the Newton Institute, having spent August to December there as a Simon's visiting fellow in Cambridge. But he's also spent time on sabbatical at Melbourne and has been awarded the J.H. Mitchell Medal as well. So Scott works in lots of areas in applied mathematics, interfacial dynamics, asymptotics, and math bio. And he's applied exponential asymptotic techniques to areas such as free surfaces and Healy-Shor flows. So today he's going to speak on Kelvin ship waves with a bit of exponential asymptotics. So Scott.
Thanks, Chris. Now, how's my screen there, Chris? Is that shared nicely?
That's fine. That looks great. Thank you.
Okay, well, welcome everyone. Welcome to my seminar. So the topic is Kelvin ship wakes, as Chris says. Now, I know that many of you will know a little bit or maybe even a lot about ship wakes, but I'm going to go a little bit slowly, at least for most of the talk, to make sure that everyone can follow. But before I start, I should just say that much of this work is done by my postdoc, who is Ravi Pethiagoda, and Ravi and also Tim Moroney, my collaborator, we're at QUT, as Chris says, Queensland University of Technology, which is in the city of Brisbane in Australia. And also towards the end, I promised just a little tiny bit of exponential asymptotics, and much of that work is due to Chris Lustry, who is at Macquarie University in Sydney, and Chris is also an organiser for this program. Okay, so what is a ship wake? Well, I'm sure everyone knows that a ship wake is the wave pattern that forms on the surface of water behind a moving object, say behind a ship or behind a duck or a boat or any disturbance. And there's a couple of things you should know about ship wakes up front. Here I've got an image. I don't know if you, hopefully you can see my mouse here. There's like a plan view of a ship wake here. The first thing you should know is that a ship wake is made up of two different types of waves. There's transverse waves, and these are sort of going up and down here. They move perpendicular to the direction of flow. And the other type of wave is a divergent wave, and they go out at an angle. So if you can see my mouse, I'm highlighting them there. And the other thing that, if you know anything about ship wakes, you'll probably know that the wake falls within a wedge that is meant to have this angle, say half angle really, of arcsin 1/3, which is about 19.5 degrees. And I would call that a Kelvin angle, or I might call it a Kelvin angle throughout the talk. So another thing I wanted to say about this image here is that this has been generated with a simulation, and it's with a toy model. And I will talk about a few toy models. In this particular toy model, there's no actual ship in the simulation. Instead, there's just a pressure that's been applied on the surface. And so it's the pressure that's moving along at some constant speed. But even though that this is a toy and this pressure is sort of acting as a proxy for the ship, that these toy models do quite a good job of illustrating most of the key features of ship wakes. And maybe I'll talk very briefly about more complicated models later on. So I do have two parts to the talk, part 1 and 2, and this is part 1. I'm just going to just give an overview of ship wakes and talk about a few of a bit of more recent research in this area. Okay, so I think I've just really mentioned this, but I can just mention it again, that it's commonly known, and most people who are in this program have probably picked up on this somewhere, at least in their life, that a ship wake is enclosed within a wedge with a half angle, which is arcsin 1 on 3, about 19.5 degrees. And that comes from a model, and I'm going to go through a derivation of this in a moment. But one thing I'll just say up front is that while this is certainly true that this angle does come out of the analysis, that even by eye, it often just doesn't seem right. So here are a couple of experiments by a French group in 2014, and there's two photos here. The photo at the top, they're pulling along just a cylinder, I think. It's just a cylinder in a swimming pool, and it's at some moderate speed, and they measured the wake angle here. And for the top photo, the wake angle did line up very closely to this Kelvin wake angle. But in the bottom photo, they're pulling their cylinder along much faster, maybe 2.5 times faster or something. And then they measured the wake angle in this bottom case here, and that angle was about half of the Kelvin angle. So I think that this is just a simple example, but it is reasonably well known that often it just doesn't seem right that this particular Kelvin angle. And again, the same group, these French researchers wrote a PRL paper in 2013, which is reasonably well known now. And they did something that's cool, which is to trawl through some Google Earth data and find images of ships that are in deep water, and you can measure the wavelength of the transverse waves, and that gives you a good estimate of the speed of the ship. And they measured the wake angles, and so then they've had all this data here. You can see a sort of a plot here of the y-axis is the wake angle, and the x-axis is effectively the speed of the ship. And they found that for moderately fast ships, the wake angle was that Kelvin angle. This is in deep water, the same angle, this one up here at the top of the slide, or thereabouts. But for sufficiently fast moving ships, they found that this apparent wake angle, the angle that they measured at least, was less than the Kelvin angle and seemed to decrease like 1 on the speed. I mean, the dimensionless number we use here is the Froude number, U and root GL, and I'll mention that in a moment. But so here on the x-axis, which you probably can't see, it's too small, is the Froude number. But anyway, with all of this data, they did show that this wake angle, or at least the apparent wake angle, the one that they measured, was decreasing like 1 on the Froude number. Okay, so here's just a few more images, and I just want to say a bit more about ship wakes generally. Here is a duck. It's not a very good image, really, but you can see the transverse waves. These are the ones that are perpendicular to the direction of flow. You can see them quite clearly. This duck's probably traveling along at a reasonable duck speed, which wouldn't be too fast. And here is a simulation from one of these toy models, and this is just meant to be set up so that it kind of mimics that wave pattern behind the duck. This toy model is actually different. It doesn't have a pressure that's applied to the surface, but instead there's a submerged source. So there's a point source singularity that's submerged just underneath the surface, and it's moving along at some speed. But in any event, you can see here in this simulation that the transverse waves are very clear, and also the divergent waves are pretty clear in this image. This second photo is of some other boat stolen from Wikipedia or somewhere, and maybe the ship's traveling faster, and you can see that the divergent waves are more prominent. And here is a simulation, which is the same toy but with a higher Froude number. That means that the ship, inverted commas, or the proxy for a ship is moving faster. And if you compare these two, you can see that the divergent waves are more prominent in the second one than what they are in the first one. So this is also well known that for faster moving ships, divergent waves are more prominent, and for more slowly moving ships, it's the transverse waves that are more prominent. Okay, so for whatever it's worth, here's another image stolen from Wikipedia, probably a very fast speedboat or something. And here's that same simulation for a very high Froude number. So that's, again, like a proxy for a very fast moving ship. And in this case, it's a little bit hard to see because it's a plan view, but this wake is really totally dominated by the divergent waves as opposed to the transverse waves. So, I mean, just for this slide, I'm going to just lay out the equations for this toy model, for one of the toy models. So throughout the talk, I'll mention these toy models numerous times, and there's 3 of them that the main ones that I'm going to mention, and I'll just sort of swap between them for no particular reason. But in all cases, the model comes from linear water wave theory, or at least this one does. There's a velocity potential phi, and phi satisfies Laplace's equation in the flow regime, or at least now that's the surface has been linearized to be z is equal to 0. There's 2 linearized boundary conditions at z is 0. The first one is a kinematic condition, which is just saying that fluid doesn't pass through its own boundary. And the second one is a dynamic condition, which is effectively a linearized version of Bernoulli's equation. It states that pressure is atmospheric pressure, except, say in this case, there's some other additional pressure that's been applied to the surface, and that additional pressure is the thing that's acting as a proxy for a real ship. So this toy doesn't incorporate any real features of a ship hull, and that's one of the negatives of the toy model. Typically, we use a Gaussian pressure distribution just because it has a nice Fourier transform. So you can imagine a Gaussian pressure moving along at some constant speed. And as I mentioned before, that this very important dimensionless number is the Froude number, which is the speed of the thing. If you think of the speed of the ship divided by root GL, and L is a length scale in the problem, like it could be the length of a ship, but in this case, it's some length scale associated with the pressure distribution. And there's some sort of strength of the pressure, which is not important. Okay, now there's a lot of noise here, but I can just say that you can solve these linear problems exactly with Fourier transforms, for example, and that you'll get some ugly looking double integral that describes the near field behavior. And I'm not so interested in that for a couple of reasons, but one of them is that this is just a toy model anyway, and that we don't have details of a hull, so I'm not so concerned about what the near field is. And then there's another integral, which is a single integral, and that captures the far field behavior. And I've got it in blue here, so if you sort of blur your eyes and ignore all the black stuff, what I'm saying is that the surface elevation or the wave height is really described, putting aside all the other noise, by a single integral of this form. Okay, so let me write that out again. And so now I'll just say, okay, that was for that particular toy, but actually for that toy or any of the other toy models that I'm interested in, or if, say, you had a more complicated model that was, say, a combination of sources and sinks or pressure points or pressure distributions, Or if you had an even more complicated model, like that comes from Mitchell's thin ship theory, all of them, they end up giving you a far field that is given by an integral of this form. So, okay, so there's different detail, of course, but really they all look like this, and this is a good starting point for analysing ship wakes. So there's an integral of this form, and there's this little function here at the front, a of psi, an amplitude function that I'll refer to a number of times. So now what I want to do is I just want to analyse this integral, and you'll see here there's an x and y. And so if you go a long way away from the ship, x and y become large, and so this thing looks like it's ripe for method of stationary phase. So let's do that. So if I let this thing in square brackets be g of psi, let's say I let x be r cos theta and y be r sine theta, then I get this integral here that, if you can see my mouse, I'm trying to circle. And this is method of, in the textbook form for method of stationary phase. So the sum integral of a of psi e to the I r of g of psi. So what I'd want to do is I'd want to find points where the derivative of g is equal to 0. And so I can do that. Here's my g. It's just a little bit of algebra. And that you'll find that there's two roots to that equation. So there's 2 points for which the derivative of this function is 0. And that's because you get a quadratic for this tan of psi. And now if I look at that formula, here I get 2 roots, and that 2 real roots when the term under the square root sign is positive or 0, I get 1 root. So it's positive when 1 minus 8 tan squared is positive, and that is when the angle theta is less than that theta wedge, which is arctan 1 on root 8, which is the same as arctan 1 on 3, sorry, arcsine 1 on 3, if you can quickly do a right angle triangle in your head, and that's this 19.5 degrees. So this is one way that you can derive this angle. If you just look at this schematic here for a moment, okay, so I'll put up another schematic soon, but here there's an observer here at XY. Here's the ship, but the waves that you see at the observer were caused by the ship before, and they came when the ship was over here. And this is the angle of psi that I'm talking about in this interpretation. Okay, so I'll just keep going with this idea and just note that, well, okay, you normally get 2 roots, but you get 1 root for one particular value of psi. So if you have a look at this figure here for a moment, so there's one special value of this wave angle of psi. It's arctan 1 on root 2 or something, 35 degrees. And so now I can see that the 2 roots appear on either side of this critical value. And so for psi less than this critical value, I get the transverse waves, and for psi greater than this critical value, I get the divergent waves. So this method of stationary phase is now giving me the wedge angle and is explaining why there are 2 different types of waves in the wave pattern. So here I've just written this integral again, and this g again. I mean, if anyone's following closely, which I'm sure they're not, but they see that I got these from the previous slide. And if I just write out the result from method of stationary phase, it looks like this. I mean, anyone who knows about this will recognize this is just in the standard form. You know, you get the same form every single time you do this method. So things to note are that you get a scaling of 1 on r to the half, because r is the large parameter in this expansion. And so the amplitude of the waves decay like 1 on r to the half. R appears in this argument here as well. Also, there's a phase shift of minus pi on 4 or pi on 4. So the first term is for the divergent waves, and the second term is for the transverse waves, and that's because, if you remember, there's 2 roots to that equation, so you get 2 contributions. The phase shift comes, I mean, as you know, okay, method of stationary phase, it's the same as going over a saddle, but if you just, you know, rotate the, deform the contour by rotating it by 45 degrees either this way or that way, depending on whether this second derivative is negative or positive or something like that. So that's where the phase shift comes from. Okay, and if you wanted to, you could just do the same. You could apply the method on the wedge angle, on the cusp or the caustic. The first derivative is 0, but also the second derivative is 0 there as well. So for whatever it's worth, you get a scaling like 1 on r to the third, which is meant to be larger than 1 on r to the half. And even outside of the wedge, there might not be real roots to this equation, but there are complex roots. So you can just deform your contour to go over the saddle, and you'll have to sort of rotate the thing at some angle. So when you do that, you'll get the same looking creature, which is a scaling of 1 on r to the half, just like before. You'll have some sort of trig term here. You'll have a different phase, and that phase will depend on like the phase of the amplitude function, which will be complex now. But importantly, you get an e to the minus r bit. So that means that the waves decay exponentially in r outside of this wedge. So I'll summarize that in a moment. But another thing I'll just say is that just with this method of stationary phase, then you can draw crest lines. So when you get two terms like this, I've just written one of them down. You've got the cos term here, so the crests you think are when, that cos term is 1, so you get the thing in square brackets and let it be equal to 2n pi. And that'll give you, because this root of psi 1 depends on theta, that'll give you r as a function of theta. And this whole thing here is for the divergent waves. You could do the same thing for the transverse waves. And so then you get these red curves, these crest lines. So the image on the top and the left is just one of these simulations of one of the toy models. And the image on the right is the same simulation, but we've drawn the crest lines over the top, and the crests here where in the lighter color, you can see that the crest lines really do follow the crests in the image. You can almost see that, but you should take my word for it. And that's true for both the transverse and also the divergent waves. And even these waves outside of the wedge, you can't see them here, but if you did a log plot of them, you could. And these lines do follow the crests very well, even though the amplitude is exponentially small. Okay, so if you're following any of that, or even if you're not following, here's a summary of this, that if you apply method of stationary phase or a bit of saddle point, you can get out the wedge angle arcsin 1 on 3. I'm going to call that the Kelvin angle. You get out of it that inside of that wedge for theta less than the Kelvin angle, you get two types of waves, the divergent waves and the transverse waves. You get their scaling of 1 on r to the half. Even on the cusp, if you wanted to, you could do this. You could find that the elevation scales like 1 on r to the third. You could do something more sophisticated than that around the cusp, of course, but just for the moment, I'm just writing this down. Even outside of the wedge, you can show that the elevation scales like 1 on r to the half by e to the minus r by something, so exponentially small in r. And that's a fair bit of information, I think, out of that. Now, everything I just said then applies for all of these solutions, regardless of the amplitude A. And the ship, the details of the ship or the model or the duck or the cylinder or whatever it is, they're all embedded in that amplitude function A. And so all of this holds, and that's why you get regardless of A, and that's why these ship wakes look the same. Like they have the same crest lines, regardless of, well, not regardless, but it appears to be regardless of what's causing the disturbance. But that seems to be provided the thing's not traveling too fast. So if I go through this analysis, I think, well, the picture seems clear enough, except that there must be something missing, because I need an explanation for why this apparent angle is less than the Kelvin angle. Okay, now I'm trying to look at the time here. I know I just started a few minutes late, but also I just thought I'd say that you can get all this information actually, or pretty much all of this information, even without method of stationary phase. And all of the old textbooks have geometric arguments like this one. So the important thing about water waves for in infinitely deep fluid is that the group velocity is half of the phase velocity. And you can get that by the dispersion relation, which says that the frequency squared is gk, where k is the wave number. The phase speed is omega on k, and the group speed is d omega dk. And you'll see then that the group speed is half of the phase speed. So that's a very neat result. That's true for water waves on an infinitely deep fluid. So now I just want to talk about the schematic here. I'll see if I can just try to describe this. So if you're looking at this image here, O here is meant to be where the ship is. So imagine there's a ship at O. It used to be at M. And so if you are an observer at S, you're in the wake, you're in the waves, but the waves that you feel now were created before when the ship was at M. So now let's say that this distance between O and M is the speed of the thing, u by some time t naught, okay? So just say if that distance is u by t naught, and that there's a wave going in the direction of the observer, then it's going to travel the distance u t naught cos of psi, and this is this angle again at psi. But the idea of this geometric argument is that, well, the observer should see waves propagating at group velocity, so that would be half of u t naught cos of psi, and so that gives you that distance, sorry, half of u t naught cos of psi. And now you've got these distances. You can write down coordinates for an observer, and here they are. And with a little bit of rearranging, you can show that these points that an observer must be at for a steady ship wake must follow that semicircle. So if it wasn't an infinitely deep fluid, if it was a finite depth fluid, or if it had surface tension or something else, then it wouldn't be this very neat semicircle. Okay, now if you go through this whole argument all over again, you can imagine, well, there'll be another semicircle here where the ship used to be at a different point, let's say n, and waves will propagate through to that observer. So there'll be two different circles for which this can happen, and that's because there are two different types of waves, transverse waves and divergent waves. These semicircles will sort of kiss a line, and that line is at an angle that you can show to be the Kelvin angle. So without going through all the detail entirely, I'm just saying that this type of argument is in all the textbooks, and you can show that that same angle, arcsin 1 and 3, comes out. You can also draw crest lines with this type of argument. The thing is that you don't get the phase shift that you get from method of stationary phase. So the phase shift is out by pi on 4 and one way and the other way. So when you draw them on top of an image, it doesn't quite go on top of the crests. It kind of misses it a bit, but still does a pretty good job. Okay, so I mean, this is really just an introduction to ship waves, but if all of that's clear, then why do Marc Ribot and Frédéric Moisy and others see wakes with smaller apparent wake angles? So that seems to be a reasonable question. And I mean, the answer really is that this amplitude function, which is the function that sort of has encoded with it all of the details of the ship or the wave maker, it also depends on the speed. It depends on the Froude number. Now, this geometric method that I just mentioned, the one in all the textbooks, it's silent about amplitudes and speeds, but method of stationary phase is not. It has this amplitude in it. It's in blue here. So the answer to this conundrum is that the amplitude function itself there, which is coming out the front, it depends on the speed. And now you might imagine you're at that particular psi, the critical psi, which corresponds to the Kelvin angle. If you're at that angle and that amplitude is 0 or almost 0, then you won't see any waves at that angle. And this happens for large Froude number. So I'm trying to illustrate that point here in this image, this plot. So this is one of these amplitude functions versus the wave number. And the dotted line here is showing this critical wave number. So that corresponds to the theta that is at the cusp, at the very edge of this Kelvin wedge. And here are 3 different wave amplitudes for 3 different Froude numbers. So that means 3 different speeds. And this is for a toy model. And from left to right, the toy's going faster and faster. Well, in this case, the submerged source is traveling faster and faster. And so for the very fast one, the one on the right, the orange one, the amplitude at this special angle is effectively 0. And this is an explanation for why you don't see waves at that angle. In fact, you only see waves that are much closer to psi pi on 2, which is much closer to theta is equal to 0. Okay, so I've got here 2 more of these images. They look very similar. They're just for 2 of these other toy models, like a pressure on the surface or a submerged doublet, which is the same as a submerged sphere traveling through the water. And you get the same behavior, which is that for large Froude number, the amplitude is negligible at that special angle. So here, for sufficiently large Froude number, the amplitude function is very small, and the peak for theta is much less than the wedge angle. And that's an explanation for the apparent wake angle being less than the wedge angle for Froude number much greater than 1. When in practice, we could try to just observe this by imagine that when these people are trying to measure angles from experimental data, what they're probably measuring is the highest peaks. They're looking at the highest peaks of the wake and they're measuring those. So with a simulation, you can just line up the highest peaks and put a line through it and measure the angle. And here's some simulations where we've got slow, faster, even faster, and very fast. And we've lined up the peaks, and you can see that the peaks correspond to an angle that is decreasing for large speeds or large Froude numbers. And in this image down here, this is from a simulation, but it looks just like that experimental collection of data where I've got an apparent wake angle, and on the x-axis I've got a Froude number. And for moderately fast ships, the wake angle is like the Kelvin angle, but for very fast ships, it drops off and decreases like 1 on the Froude number. So this is a log-log plot, and it follows that line. And you can predict precisely what it should be by analysing the far field. And I haven't shown the detail here, but you can write down the proper scaling with the prefactor for each different toy model. Okay, these are just some results from a paper of ours, but also another key paper written just before ours was by another French group, and there's other papers. There's a number of papers on this topic that are interesting. Okay, well, I think that I don't have time to this, so you could do this for finite depth. So I'll just miss this extension out, and also you can generalize this to include fully nonlinear models. They don't have to be linear models, but I'll miss that out as well. But I will just talk about this extension, which is, I think it's important to acknowledge that these toy models really don't incorporate any features of a real ship. Maybe the next best type of toy would be a pressure at the 2 pressures, a positive pressure at the bow and a negative pressure at the stern, or maybe a positive source at the front of a submarine and a negative source at the stern of a submarine. In that case, you get an amplitude function that looks like this. Or an even more complicated model from Mitchell's thin ship theory gives you an amplitude function that looks like this. And there's wave interference between waves created at the bow and the stern, and they make this amplitude function go to 0 at certain values of psi. And so really what's happening is that the story is more complicated than what I've been suggesting when you take into account wave interference. And I don't have time to go on about all that, but the scalings are slightly different, and there's other interesting aspects to the problem. But I just think that the toy models really do illustrate many of the key features, but not all. And that if you want to incorporate wave interference, then you're going to have to change your model to be something more sophisticated. And these French groups, they also did this with pressure distributions and got the same sort of results. Okay, another extension, which I wasn't going to talk about anyway, but to show an image is for, we could have accelerating ships or ships going around different paths, and you can draw crest lines and so on from method of stationary phase, and that's interesting. Okay, well, that's part one, and I'm sort of lost for how much time I've used up, but part two is to kind of revisit the same ideas, but this time, instead of all this focus on ships that are traveling sufficiently fast, what about ships that are traveling very slowly? Okay, so I think that's a good point for me to have a drink of water. I think everyone knows that people don't concentrate for more than half an hour. So from this point on, I can probably assume that I've lost you, and especially on Zoom, that can happen. But if you bear with me, let's talk a little bit about the other limit, not fast-moving ships, but slow-moving ships. Okay, so here I say, okay, instead of fast-moving ships, that's when the Froude number is much greater than 1. Let's talk about the other limit when Froude number is much less than 1. And so just as a bit of a starting point here, I've got an image here which is of a ship wake generated for a very small Froude number. So it's 0.2 in this case. It's for one of the toy models, and it's for when there's a submerged source that's moving along at some speed. And what you might notice is that you can't see any of the divergent waves. So when the Froude number is small enough, the divergent waves appear to just go away. Now they are there, but they're exponentially small compared to the transverse waves. Now, just as a bit of a warning for myself and anyone who wants to do this, okay, if you're going to take the limit f goes to 0 in any of your analysis, then you should know that if we did include surface tension, then there'd be a lower bound on the speed. And it's about 0.23 meters per second. And in that case, there'd be a dimensionless surface tension parameter, which is given by this. Putting aside the detail, just say that this dimensionless surface tension parameter is 1 on 4. So even if you don't want to include surface tension, which I certainly don't, if you take Froude number goes to 0, at some point the Froude number is going to be small enough that it would mean that in dimensional terms, the speed would be less than 0.23 meters per second, and that's just not going to be too physical. So a little bit of care is needed with the physical interpretation of this limit f goes to 0. But I think, like, here's a good type of example that if you had a ship traveling at 1 meter per second, but it was a reasonably large ship, like a cargo ship or something that was 5 meters long, then the Froude number would be 0.14, which is quite small, but the surface tension parameter would be like 10 to the minus 4, which is much less than a quarter. So you can have reasonable regimes where the Froude number is small, but surface tension is still negligible, provided that you're talking about really like big enough ships. So in a sense, the limit is larger ships, not smaller speeds. Okay, enough of real numbers. So here are some images at the top of one of these toy models, and what I want you to look at is, just say if you look at the third one for a moment, that's just for a moderate Froude number. I talked about these at length before in the first part of the talk. You can see the transverse waves, and you can see the divergent waves. And this dotted line in this case is the Kelvin wedge angle. But the left two images are for small Froude numbers, and here you can't see the divergent waves at all. In fact, for the one on the very left, for Froude numbers 0.1, you can hardly see anything except for just a little, like the transverse waves I can see on my screen, but I hope that you can see as well. And in the left two cases, the dotted line is not the Kelvin wake angle, it's just some other angle where I've tried to sort of fit it to, say, a height, which turns out to be like 20% of the maximum wave height. Now, I've sort of put this figure in the wrong place. It occurred to me, but it's too late now. If you take a slice of one of these transverse waves, so you look at one of these transverse waves, and now you look at the cross-section of that, what happens is that the maximum of the wave for small fluid number is at theta is 0. So the wave goes up and then goes down again. And so you can't use this idea of a apparent wake angle being defined by the maximum wave height, because here that would just give the angle of 0. So I think we need a different type of way to say that at least that we're going to measure apparent wake angle, and it could be of a percentage of the maximum height. So another thing you can see from this image is that as the fluid number gets lower and lower, that this wave just gets squeezed into the center. So it looks like that the waves narrow as fluid number decreases. So I'm going to talk more about this for a few more slides, but what I'm suggesting is that before I said that the wake angle, apparent wake angle, decreased for very large fluid numbers, and now I'm going to say it also decreases for very small fluid numbers, but for very different reasons. Okay, so I think that you can get a lot out of this just from, okay, back to method of stationary phase, but don't worry about the detail. You've seen this sort of thing before, and these grey equations in the middle are greyed out so that you can ignore them. So there's some detail with method of stationary phase, but just so very crudely, what if I just write it like the bottom equation, which is in blue, and that gives you a sense of what's going on here. So the waves scale like 1 on r to the half, but they've also got a 1 on fluid number out the front. But the important factor here is that we've got an e to the minus something on f squared. So the amplitude of these waves when the fluid number goes to 0 is exponentially small. And also you get this sinusoidal part or a cos part, and the wavelength is like, or goes like, fluid number squared. So you've got this problem where in the limit f goes to 0, the wavelength goes to 0 algebraically, and the amplitude goes to 0 exponentially. So look, I think that this is interesting analysis from this point on, but you can imagine that it's going to be difficult to observe this type of behavior in a real experiment. Okay, you could draw crest lines, and you can see from the analysis that I'm not going through the detail of, that the divergent waves are exponentially smaller than the transverse waves. So just thinking about transverse waves, you can draw the crest lines, and if you draw a crest line, you can get the wave height, and the wave height is like that image a few slides ago, the one that I mentioned I probably should have put somewhere else. So it goes up and then it goes down, and that this wave profile squeezes in as fluid number gets smaller. And when you do this, you might say define an apparent wake angle as, say, like that. Let's say the height was 20% of the, or 0.2 of the maximum height, then alpha would be 0.2. And if you do that, you can analyze this far field behavior and show that this apparent wake angle decreases like the fluid number for one of the toy models and like the fluid number squared for another one. And so now I have more of a bigger picture here. This image here is apparent wake angle versus fluid number like before. And like before for large fluid number, I had the wake angle decreasing like 1 on fluid number for the 3 different toy models. For moderate fluid numbers, I've got the wake angle being roughly the same as the Kelvin angle. And for small fluid numbers, it's decreasing like f or f squared, depending on the details of the model. Okay, so as promised, here's a very little bit of exponential asymptotics. Now, you might want to write out an asymptotic series for the unknowns in this problem, which are zeta, the surface elevation, and phi, the velocity potential, in powers of f squared, the fluid number squared. But we can already see that the amplitude of the waves is going to be exponentially small in the Froude number. So this type of expansion is never going to capture the waves, you know, the leading order term or the correction term or the next term and so on. The wave amplitude is going to be smaller than all of those algebraic terms. So we'd say that the waves are beyond all orders in that sense. And if you did write out a series in Froude number, in powers of the Froude number squared, then that series would be a divergent series, and you'd have to truncate it. Now, the best place to truncate it would be to truncate optimally, say. And if you do that, then you'd know that the remainder must be exponentially small. So really it's optimal truncation and then examination of the remainder that gives you some information about the solution, about the waves. And that they're going to look like e to the minus some function chi on f squared as f goes to 0. And one of the catches with this idea, of course, is that this optimal truncation is for some n, but n depends on where you are, and it also depends on the Froude number. So it's not a trivial exercise. Okay, so look, this is me just giving a very brief summary of some of the details. In this sort of expansion here for zeta, there'd be another expansion for phi that I didn't write out. You'd know that the leading order term should be singular somewhere, and just say the toy model that we're considering is flow past a submerged source or a submerged source moving along. So just say if you're in the reference frame of the submerged source, then it's flow past a submerged source. Then that should be, the leading order term should be singular where the source is. Now, another interesting point is that as f goes to 0, this point of optimal truncation, this value of n, should go to infinity. So the information that you really want to get to is not at the beginning of this series, it's actually at the tail of it. So you might write down an ansatz for the tail of the series. And because these problems always involve repeated differentiation, you always get them diverging. Well, not always, but you almost always get them diverging in the same way, which is like some sort of factorial over power. So you could write down an ansatz that is of that form, but doesn't have all the detail in it. Maybe some unknowns like gamma, and this function chi, which is a singulant, and some other prefactor out the front, and you substitute them into the equations that you get in the limit that little n goes to infinity. And to leading order you get chi, and then you can maybe write down something for b. So for this problem, it turns out that chi, the singulant, satisfies some nonlinear ODE, and okay, you want chi to be 0 at the singularity, and so you get this kind of boundary condition here. And well, Chris assures me you can solve this equation with Sharpie's method, which gives you this exact solution. So putting aside the detail, you can get an exact solution for chi. And now we know that Stokes lines emerge from these singularities of the leading order term, and that they're found by setting the imaginary part of chi to be 0 and the real part to be greater than 0. And then the waves will in effect switch on as we cross over these Stokes lines. So the switching on will be done in a smooth way, but if you move away from the Stokes lines, it's as if they are just switched on. It turns out for this problem, the Stokes lines, at least for the transverse waves, are just at x is equal to 0. And if anyone's keen for any detail, then here's a paper with Chris and John Chapman. Okay, so when you cross a Stokes line, you'll pick up a contribution, and the analysis it looks messy for this particular problem in my view, but it seems to be the same for all of these, well, for most of these problems. And so you'll get this exponentially small term, e to the minus real part of chi over Froude number squared. You'll get a a wavy term, which is a cos with the imaginary part of chi over Fred number squared. So again, you pick up this wavelength of that goes like Fred number squared. So this wave has all of the features that you would expect. And looking at this term e to the minus real part of chi on f squared, you want to plot the real part of chi as a constant. We're interested in that. And you can do some expansion, and putting aside the details, we can relate this apparent wake angle now to this little number nu, say. And what it does is it allows us to draw envelope function. So we can draw an envelope. So if you look at this picture here at the top right, it's a small Froude number. There are these transverse waves, and this solid envelope curve comes from the exponential asymptotics. And so it's really describing where the waves are, and that it's sort of further information about this apparent wake angle, and you can show that it decreases like as f goes to 0 in the way that we predicted before. And also you can see here this dotted line is the Kelvin wake angle, and again this is you can see that the angle is not the Kelvin wake angle. This image down the bottom is another one of these ones for a small Froude number, and again the dark curve is the envelope function from exponential asymptotics. The dash curve is the Kelvin wake angle, and again they're not the same. Okay, so I think I've run out of path, but I'll just sort of say that one thing I tried to emphasize before was that for real models, we should really include more sophisticated versions of the wave maker that incorporate wave interference. And one simple way to do that would be to have a submerged source and a submerged sink that are just offset by some dimensionless distance. And here, just to show how important this is, if I offset this source and sink by some dimensionless distance of 1.89, 1.97, and 2.01, they're all effectively the same. They're all very close to 2. One of them gives constructive interference, one of them gives no interference, and the other one gives destructive interference. And the actual crests, the wave crests, if you follow one of these crests, the wave amplitude looks very different. When there's destructive interference, it's very low, and constructive interference, it's very high. So these are all for these dimensionless distances, which are all very close to each other. And it shows that wave interference is very important. For low Froude numbers, it's the transverse wave interference that's important. And for high Froude numbers, it's divergent wave interference that's important. So if you're serious about these models, you'd want to include some way to have interference between waves created at the bow and the stern of the thing, the ship, the boat, or whatever it is. Okay, well, that's me done. So here's a summary. Here's Kelvin and one of these images from the 1880 something paper. And again, you can see the crest lines and the same details. It's quite lovely. So a summary is that there's plenty of evidence that there's a Kelvin wake half angle, really. I'm calling it angle, but half angle of arcsin 1 on 3. And I spoke about how you could get that. You could get it from method of stationary phase. You could get it from geometric arguments, for example. But there's also it's also easy to see, even by eye, that for fast-moving ships, the apparent wake angle, the angle that you see with your eye, is or can be smaller than the Kelvin wake angle, at least for sufficiently fast-moving ships. You can show that that angle decreases like 1 on speed. You can do that with experiments like with Google Earth or with simulations. And the explanation for why that can be the case, when you might have thought that the wake angle is independent of speed, is due to the amplitude function, and I tried to explain that. Also mentioning that interference is important and makes the story more complicated. At the very end of the talk, I spoke a bit about slow-moving ships, and the apparent wake angle also appears to be less than that Kelvin angle. And if you neglect surface tension, you can analyze that problem with exponential asymptotics, as Chris and John Chapman did. Okay, well, that's it. And I just wanted to say thanks to the Newton Institute for having me in 2019. And also, again, to mention that my postdoc Ravi helped me a lot over the last few days to put together images for this seminar. And here are some of our publications. And if you're that way inclined, there's my Twitter handle. That's it.
Okay, thank you very much, Scott. That was a really commanding overview of recent work in Kelvin ship waves. Does anybody have any questions for Scott?
Yes, may I make a comment, a couple of comments?
Yeah.
Thank you. Well, first of all, thank you for this lecture, and particularly for the explanations of why the angle is smaller than the Kelvin angle for very fast speeds and very slow speeds. That's very nice, and particularly for fast speeds, which is the one you mostly see in terms of this amplitude function. You use the phrase toy models a lot. Just a matter of taste. I mean, I've always found that has this kind of disparaging air of trivialization about it, and they're not toy, they're not trivial at all. I mean, they describe a lot of the physics. So I follow Nigel Goldenfeld and call them minimal models. Depends what you want to explain. I mean, Kelvin's itself, I mean, that explains most of what you see, and it's pretty good. Now, my main comment, though, is the following. You use the word caustic once. Now, you also mentioned cusp, which it isn't. Now, of course, the minute you see a caustic, I mean, everybody at this meeting knows that you're going to see an airy function decorating it. And it's not at all difficult. Indeed, Ursel did it many years ago, and it's a pretty straightforward application of 60-year-old Chester Friedman Ursel uniform approximation to describe all of the interfering waves that you described, I mean, root stationary phase points, embedding them in airy functions rather than sines and cosines and exponentials. And it really instantly describes pretty well the whole pattern. I mean, if you don't do that, then you essentially, you don't describe the pattern where it's often most intense, namely if you're not going too fast or too slow across the caustic. Now, there's something else which I commend to you, which is kind of very nice if you're giving talks like you just did, and especially to students, I think, which is this. Imagine you're in a small boat and a big ship goes by. Now, of course, its wake, and including this Kelvin caustic, will come towards you. Now, two things. The first is it seems to take much longer than you expect, and that's because you see the waves, but what reaches you is the group, which takes twice as long, because as you've said, the speed is only half as great. That's one thing, but most important, when that reaches you, your little boat rocks from side to side, you feel it, and you're feeling in your body the airy function in the same way as when you look at a rainbow, you see it with your eyes. And that's a very good illustration of the universality of this airy function, which describes all smooth caustics. And I was kind of all the time crying out, waiting for you to say the word airy function, and you never did. And you know, a lot of the sophisticated analysis you describe later can also be included. I mean, this amplitude function can also be incorporated into the uniform asymptotics. You just get the airy and the airy prime with amplitudes which depend on the stationary phase points underlying the whole thing. So, you know, I don't want to be too critical, because I enjoyed and learned from your description of the very fast and very slow. But, you know, is there a reason why you didn't use airy functions?
Okay, thanks for that, Michael. So just for the first point, I think that I'm in a bad habit of calling these models toy models, and I sometimes try to get out of the habit, but I just seem to fall back into it. And I don't think you're on Twitter, but people have mentioned to me recently as well that I understand that point, and you see, they seem like toy models to some extent, but I understand, of course, that they're not meant to be just games. So that is a well-made point. Well, you might have noticed that I did sort of just mention, well, I mean, that I just sort of said, well, for whatever it's worth, we could apply this method of stationary phase on that particular angle.
No, you did.
Because I didn't want to muddy the overall picture, and I also sort of mentioned in passing that you could clean it up. I think I might have mentioned that you can clean it up by doing a better job of that. So yes, I do take the point that it might have been better done if I included the Ursel analysis, which obviously, I mean, the way that I mentioned it, it didn't make any sense, of course, because it scales like 1 on r to the third at a very line, and then r to the half inside the wedge. And I understand that it's very crude, but I just thought that was going to just make the point.
Yeah, okay. I mean, I would say that it's not muddying the. It is the ARA function is the essence of this phenomenon. It's the thing that, when you're not going too fast or too slow, it's one of the things that you most dramatically see is the pattern as you go across, as you say, the transition from the two types of waves. By the way, I mean, you talked about interference quite a bit, and I know what you mean by that. But of course, the original Kelvin pattern is also interference. I mean, those waves that you see are inside the wedge are the interferences between the two stationary phase points. That's what they are. Well,
yeah, in his original paper, I did attach one of those images. You might have just saw.
Yeah, I saw.
I did not attach the ones later on, and they clearly have the interference pattern is clearly shown in that sketch that he includes.
Yeah, it's just terminology. I mean, what you describe is additional interference, very important between the front and the back or whatever. Anyway, never mind. But thank you very much. Thank you.
Any other questions?
Just to follow on Fritz Ursel stuff, he's written a lot about this. My impression was that Ursel stuff was so Ursel and Keller wrote about this, and their source might be on the surface. And I'm curious, if you submerge the source, is it still the ARA? The ARA theory is always there, but do you change the location of the caustic into the complex plane if you submerge the source versus if you keep the source on the surface itself?
No, I don't think that. I don't think it changes that. I haven't done the source on the surface. I know that's Chris and John took the limit. They had an extra parameter so they could take the limit that their source went up to the surface. And, I remember reading that was to match up with Keller's paper, but I had not seen that source on the surface. I think that it's all going to be the same, in effect, regardless of the wave maker, the cause of the wave, whether it's a submerged source or some other minimal model for a ship.
I mean, if the source is on the surface, you have issues with the analysis of the integral equation right behind the track so there's some very complicated asymptotics that you have to do, I think, right behind the track of the point.
Yeah. So we want to avoid, we avoid, say, point pressures. We avoid having a source on the surface. That's why we've got a pressure distribution and why we've got the source submerged. So I think that we've been deliberately avoiding those so that the solution is very smooth and nice looking, whereas the point pressure gives sort of weird stuff. And I assume the point source on the surface might give rise to some weirdness as well. I'm not as familiar with that as what I probably should be.
I can explain actually where the ARAs go when you submerge it. There are still ARAs. They actually coalesce when the source hits the surface, but when they're off, they sit in the analytically continued complex plane. There's 4 of them. And you can show that everything you see with the 2 different kinds of waves is different bits of the ARA behaving in a certain way.
Shall we switch off the recording now and then other people can ask other questions?